Hello viewers, this is Walker Ronald taking you through the story of A-level applied mathematics. And in this video I'm going to talk about the topic of equilibrium of suspended particles and rigid bodies. So this topic is in mechanics and is suitable for students in senior 5 and senior 6 offering principal mathematics. So it can be suspended particles or suspended rigid bodies. So we shall start with case 1, which involves suspended particles, and the case 2 will involve suspended rigid bodies. So for suspended particles, when they are in equilibrium, the condition is that the resultant force must be 0. Now resultant force being 0, it means that when you resolve horizontally, forces to the left are equal to forces to the right, and when you resolve vertically, upward forces are equal to downward forces. So with that knowledge, I'll go to this question. Question 1 came from UNEB of March 1998 of paper 2 of question 4. And it says that a particle of weight 8 newtons is attached to point B of a light inextensible string AB. It hangs in equilibrium with point A fixed and AB at an angle of 30 degrees. To the downward vertical. Now that word, downward vertical. A force capital F at B acting at right angles. Now that word, right angles to AB keeps the keeps the particle in equilibrium. This is the most important keyword, equilibrium. Then they say that find the magnitude of F and the tension in the string. So the first thing to do is to draw a force diagram. So the string is inclined at that angle of theta to the downward vertical. This is what they mean by downward vertical. Then this is the particle, and this is the string AB. So forces, the first force to put will always be weight, and weight acts vertically downwards. The next is to show the force. They told us the force acts at right angles to the string, so that is why this is 90. Now from geometry, if this is 30 and this is 90, it implies that this will also be 30. The next is to show the tension in the string. As long as there is tension, the arrows must point towards each other. So how to finish the first diagram, next we shall resolve vertically and horizontally. So remember we said when you resolve horizontally, forces to the right are equal to forces to the left. So in this case, this tension acts horizontally, it acts to the left, and this force horizontally, it acts to the right. So when I resolve this to the horizontal, it will be t sine 30, and this to the horizontal, it will be f cos 30. So this is t sine 30 because the angle is on the vertical. I think you see this angle is inclined to the vertical, meaning that this is 30, and when you are resolving, where the angle lies is what becomes cos. Now since the horizontal, the angle does not lie on the horizontal, it implies that the horizontal component will have sine, so that is why there is sine here. But for this other force capital F, the angle is lying on the horizontal, meaning the horizontal component will have cos. That is why you see cos there. So next is to simplify. When I bring this one this side, I realize that sine over cos gives me tan, and that is why F is equal to t tan 30 degrees. Then I will also resolve vertically. Vertically, I remember that upward forces are equal to downward forces. So the only downward force is this 8 newtons, which is there. Now the upward force, still I will resolve this tension to the vertical, and remember this angle lies on the vertical, meaning the vertical component will have cos. That is why there is cos there. And this one, the angle lies on the horizontal, meaning the vertical component will have sine. That is why you see sine 30 there. Then I already know f in terms of t, so I'll come and substitute for f here. Then after that I realized that t is common, so I'll factorize it out, and in the end, in this step I have only t, which is the only unknown. Therefore t will be equal to 6.9282 newtons. Now from equation 1, this equation 1, we can be able to get our value of f. So capital F is equal to this t, which is that, and this tan theta, which is that, and then I'll come up with 4.0 newtons. So basically that's what they wanted. Now let's see how marks can be awarded. So B1 for horizontal component, another B1 for resolving vertically, M1 for substituting for F, and A1 for the tension, A1 for the value of capital F. So now we shall go to question 2. Question 2 came from UNEB 2002, paper 2, question 12, and says a particle of mass 3 kilograms is attached to the lower end B of an inextensible string. The upper end A of the string is fixed to a point on the ceiling of the roof. A horizontal force, know this word, horizontal force of 22 newtons and an upward vertical force. So we have a horizontal force and an upward vertical force of 4.9 newtons act upon the particle, making it to be in equilibrium. So this is the most important keyword, equilibrium. With the string making an angle alpha with the vertical, find the value of alpha and the tension in the string. So the first thing to do is to draw a force diagram. So the weight, it will be 3g because the mass was 3 kilograms. Then they talked about a horizontal force, which is 22 newtons. And they also talked about a vertical force, which is 4.9 newtons. And this angle is to the vertical. If you look at this, makes this with the vertical, so that is why there is alpha there. The next is to put tension in the string. As long as there is tension, the arrows must point towards each other. That is why you see these arrows pointing towards each other. So always when there is tension, arrows must point towards each other. So that is the first diagram, and that is 1 mark, as long as it is drawn using a ruler. So next is to use this first diagram to answer the questions. Remember, for equilibrium, we have to resolve vertically and horizontally. So I'll start by resolving horizontally, and I'll come up with t sine alpha is equal to 22. Let's see where that comes from. So t is here, so when I resolve that tension horizontally, remember the angle lies on the vertical, meaning the vertical component will have cos, and therefore the horizontal component will have sine. That is why it was t sine alpha, and it is equal to this, because this is going to the right and this is to the left, so they have to be equal. Vertically it will be, the component of this tension will be t cos alpha. It goes upwards, and also this 4.9, it also goes upwards, but downwards there is this 3g, so these two will be equal to 3g. So you come and say that we're also resolving vertically. T cos alpha plus 4.9 is equal to 3g, but g is equal to 9.8, therefore I'll come up with equation 2, which is t cos alpha is equal to 24.5. Then I'll divide, because these are two equations and two unknowns, meaning you have to solve simultaneously. So when I divide equation 1 by 2, I'll come up with that. So this t sine alpha is this, then t cos alpha is there, then on the right hand side 22 is here, and this 24.5 is there. But I know that sine alpha over cos alpha is equal to tan alpha, and this t cancels. Therefore, I'll come up with tan alpha being equal to 22 over 24.5, implying that alpha is equal to 41.9225 degrees. But they also wanted the tension in the string, so I'll come back and from equation 1, I'll substitute for alpha and be able to get the value of tension, which is 32.9280. So basically that's what they wanted. Now let's see how marks can be awarded. So B1 for equation 1, B1 for equation 2, M1 for this division, A1 for the value of alpha, A1 for the value of tension. So that has been question 2. Now we shall go to question 3, which came from UNEB 2003, paper 2, question 14, and it says a particle of weight 24 newtons is suspended. So this word is suspended by a light inextensible string from a light ring. Now this, we have brought a new term, ring. This one is you have to be careful while answering such a question with a ring. So the ring can slide along a rough horizontal road. Know that word. The coefficient of friction between the rod and the ring is 1/3. A force of P newtons acting upwards on the particle at 45 degrees to the horizontal keeps the system in equilibrium. So this is the most crucial word. With the ring at the point of sliding, meaning it's in limiting equilibrium. Find Roman 1 the value of P, Roman 2 the tension in the string. So you start by drawing a force diagram. So that is a ring. Then we have a string inclined at an angle alpha to the vertical. Now this is the particle, but they said it's of weight 24 newtons, so it will, remember, weight acts vertically downwards. Then there is a force P, which acts at an angle of 45 degrees to the horizontal. Then there will also be tension in the string. I told you when there is tension, the arrows must point towards each other. Now that is for the particle, but what about for the ring? For the ring here, there is normal reaction, and they told us there is friction here, so there has to be friction, which is mu r, where mu is the coefficient of friction and r is this normal reaction. So now we shall go to Roman 1. So for the ring, now consider these ones separately. So for the ring, these are the forces, and for the particle, these are the forces, so we consider them separately. Now shall begin with the ring. So for the ring, when you look at this ring, we have to resolve vertically and horizontally. When I resolve horizontally, this force is going to the left, and the component of this tension goes to the right. But remember, the angle lies on the vertical, meaning the horizontal component will have sine. That is why there is sine alpha there. So when I substitute for mu, I'll come up with that. Therefore, make r the subject, it will become 3t sine alpha, and that is equation 1. Then I'll also resolve vertically. So when I resolve vertically, still on the ring, I realize that this r is going upwards, but this component of tension goes downwards, and it will be t cos alpha. That is why you see t cos alpha there, because the angle lies on the vertical, meaning the vertical component will have cos alpha. So next is to solve these two equations simultaneously. So when I divide 1 by 2, I'll come up with that. and in the end this r and this r becomes 1, which is there, and this cancels, then you remain with 3 tan alpha, which is that. Now before I go to the next slide, let's see how marks can be awarded. So B1 for the correct first diagram drawn using a ruler, B1 for equation 1, B1 for equation 2, M1 for division. So when I make tan alpha the subject, it will become tan alpha will equal to 1 over 3. Therefore alpha is 18.4349 degrees. Now that was for the ring. Now for the particle, you also have to resolve vertically and horizontal. So when I resolve horizontal, I'll come up with t sine alpha equal to p cos 45. But cos 45 is equal to root 2 over 2, which gives you 0.5 p root 2. Then when I resolve vertically, I'll come up with t cos alpha plus p sine 45 degrees equal to 24. But sine 45 is equal to root 2 over 2, which gives you 0.5 root 2, and this p which is there. That gives me equation 4. So I have 2 equations and 2 unknowns. So when I divide 3 by 4, I'll come up with this part, and I realize that this and this cancels, then this and this gives me tan alpha. But I already know that tan alpha is 1 over 3, so I'll come and substitute for tan alpha, and then I cross multiply, and with this I realize that there is only one unknown, so I'll have to collect like terms, and after that make p the subject. So p is 6 root 2. Remember, you can't leave your answer when the stud is in the denominator. So when you leave your value of p at this point, it means you have lost an accuracy mark. You have to rationalize so that the stud is in the numerator. So basically that's what they wanted. Now let's see how marks can be awarded for this value of p. So B1 for the value of alpha, equation 1, equation 2, division, substituting tan alpha, and value of p. So what is left is to get the tension. So we have said that from equation 1, t sine, I'll substitute for alpha, and for p to remain with t as the only unknown. Therefore t will be equal to 18.9737 newtons. So for this part, M1 is for substitution and A1 is for the value of t which they want. So that has been question 3. Now we shall go to question 4. Question 4 came from UNEB 2020, that is last year, of paper 2, question 13, and says the diagram below shows 3 strings AB, which is 15 centimeters, BC, which is 10 centimeters, and CD, which is 13 centimeters. A and D are fixed to small rings. Note this word, when each time you see this word ring, just know care needs to be taken. Each of mass 2 kilograms, which can slide on a rough horizontal rail AD. Masses M1 and M2 are attached at B and C respectively. The system rests in equilibrium, so this is the most important keyword, equilibrium, with BC at a distance of 12 centimeters below AD. So the good thing, they helped us and they drew for us the diagram. Then part A show that 9m1 is equal to 5m2. Then part B, if the coefficient of friction between each ring and the rail is a quarter, and the ring at A is on the point of slipping, determine the value of M1. Notice why that the ring at A is at the point of slipping, meaning friction is maximum at that point. So yeah, the first thing to do, we are going to redraw the given diagram, and after that we shall show the forces acting. So we shall start with the weights, remember, because weights always act vertically downwards. So the mass was M1, to be weight will be mg. Here mass was M2, weight will be M2g. Then also here the weight, the mass was 2 kilograms of the ring, so weight will be 2g, and also here the weight will be 2g. Then the tensions, like I said, the arrows must point towards each other as long as there's tension. So there is one string. Here there is also another string, so the tension will be different because the strings are different. So this is T2. And also here there is tension, so the arrows must point towards each other. And also since there's another string, so tension must also be different. So as long as the string is different, tension has to be different. So next is to show normal reaction at the ring. So here there is R1, and here the R1 and friction force, and also here there is R2 and friction. Note that here we are using mu R, but here we are just using capital F. Why? Because at this point friction is maximum, because the particles that this ring is at the point of sliding. But here we are not yet told that it's at the point of sliding. That is why you can't put mu R. So that is our first diagram. Next is to find the values of θ1 and θ2, because there's no way you can resolve when you don't have those angles. So for θ1, when I use this triangle, I realize that this is the opposite, and this is the adjacent, and this is the hypotenuse. Therefore sine θ will be equal to opposite over adjacent. We are given this as 12 and this as, opposite over hypotenuse, and this was 15. Therefore opposite 12, hypotenuse 15. Therefore sine θ is 12 over 15. Now from Pythagoras theory I can be able to get this value of the adjacent, which is square root of 15 squared minus 12 squared, which will be 9. So that means that cos θ1 is equal to 9 over 15 and tan θ1 is 12 over 9. So now we shall go to this triangle, and for this triangle, when the angle is there, it implies that this is the opposite and the hypotenuse is here and adjacent is there. Therefore sine θ2 will be equal to 12 over 13. We are given this as 12 and this as 13. That means that the adjacent can be got from Pythagoras theory, and it will be square root of 13 squared minus 12 squared, which is 5. So that means that cos θ2 is equal to 5 over 13 and tan θ2 is equal to 12 over 5. So now that we have got the angles θ1 and θ2, we can be able to resolve. So let's see how much can be avoided for this slide, then we can start our resolving. So B1 for the first diagram, B1 for θ1, and another B1 for θ2. So we shall start by resolving vertically and horizontally at B, and we shall get those values. So let's see how they come about. So at point B, the forces acting at the particle P are these ones. Therefore, when I resolve horizontally, this angle here, this θ1 is also the same as this, θ is also the same as that, because of alternating angles. Therefore the angle is lying on the horizontal, meaning the horizontal component will have cos. Therefore when I resolve horizontally, it will be T1 cos θ1 will be equal to T3. That is horizontally. What about vertically? Vertically it will be T1 sine θ1 equal to M1 G. So that is where these values are coming from, equation 1 and equation 2. So next we shall divide the two equations to come up with that. So this is here, this is here, this is here, and this is there. This T1 cancels, and this gives you tan theta 1. Therefore, I already know that tan theta 1 is equal to 12 over 9. Therefore, T3 will be equal to 9 over 12 M1G. So that has been at point B. What about at point C? We also have to resolve vertically and horizontally. So at point C, the forces acting are these ones. Therefore, if you look at this angle, theta 2 is lying on the horizontal, meaning the horizontal component will have cos. Therefore, when I'm resolving horizontal, I'll say T2 cos theta 2 is equal to T3. And when I'm resolving vertically, I'll say T2 sin theta 2 is equal to M2G. So let's write that. So that is vertically, then that is horizontally. Then we shall also have to divide both equations. So this should have been 4 and 5, dividing equations 4 and 5. So that gives me that. Therefore, tan theta 2 will be equal to that. But I know that tan theta 2 is equal to 12 over 5. Therefore, T3 is still equal to that. So before we go to the next slide, let's see how mass can be awarded. So this for resolving vertically and horizontally, and this one is for getting equation 3, and this one also resolving vertically and horizontally, and this one for getting equation 6. Now equating equation 3 and equation 6, we shall come up with that. And when I simplify, I'll come up with that, because this 12 and this 12 can cancel, so you remain with, and also this G and this G can cancel, so you remain with 9M1, and here remain with 5M2, which is that. And basically that's what they wanted in the proof. So now we shall go to part B, where they want the value of M, given that the coefficient of friction at point A is a quarter. So what we are going to do, we shall go at point A and resolve both vertically and horizontally. So when I resolve vertically, I'll come up with R1 is equal to 2G plus T1 sine theta 1. Let's see how that comes about. So if you look at this point at A, these are the forces we are interested in. Therefore, vertically, this tension, the angle is lying on the horizontal, meaning the horizontal component is what will have cos, therefore the vertical component will have sine. Now, vertically, upwards there is R1, that is okay, but downwards there are two components. There is this weight, but there's also a component of tension, which is T1 sine theta 1. Therefore, you have to add the R1 is equal to 2G plus T1 sine theta 1. That is vertically. What about horizontally? Horizontally, the component of this tension horizontally will be T1 cos theta 1, and it goes to the right, and the one to the left is mu R1, but we know mu is a quarter, therefore it will be a quarter R1. So let's go and write that. So that is resolving vertically, but we know that this is equal to that, therefore we shall come and substitute to come up with that as equation 7. Then we shall also resolve horizontally, and to be that, but mu is a quarter, and we also already saw that this is equal to T3, and T3 was equal to this, therefore we shall come and substitute. Where there is T1 cos theta 1, we shall put there 9 over 12 M1G, which is that, and where there is mu, we shall put there a quarter, and where there is R1, we shall put there this expression. And with that we can simplify, because this and this reduces to 3, then this 3 and this one reduces to give you 3 here, 3 up. So you can either do that or you can just cross multiply, and is okay. So when I reduce this by this to give me 3 here, I can bring this 3 this side to come up with this, and this 9 remains there. Then when I open brackets, I'll come up with that part, and I'll think realize that it's only m1 which is the only unknown. Therefore m1 can be got, and it will be equal to 1 kilogram. So basically that's what they wanted. Now let's see how much can be awarded. So m1 for equating, and b1 for the required proof, b1 for resolving vertically and horizontally. So this part and this part, that is b1, m1 for substitution, for substituting for this and this and that. Then a1 is for the value of m. So that has been suspended particles, but your case 2 now will be suspended rigid bodies. Now, unlike suspended particles, for rigid bodies another condition comes in. For particles it is only resultant force which is equal to 0, but for rigid bodies also the turning effect must be 0. When the turning effect is 0, it means that sum of anti-clockwise moments is equal to the sum of clockwise moment. So that is the second condition which will be added on top of resultant force being equal to 0. So with that knowledge, we shall go through question 6, and question 6 says a non-uniform ladder AB of weight 78 newtons and length 5 meters is freely suspended horizontally by 2 light inelastic strings AC and BD that make angles 30 degrees and 40 degrees respectively with the vertical. Find the distance from A where the weight of the ladder acts. Remember, it is non-uniform, meaning that the position of the center of gravity is no longer the midpoint, therefore it is at a certain point, not the midpoint. So the first thing will be to make a sketch of the force diagram. So you put the weight which is at a certain point, not the midpoint. That is why you put here D, because we don't know the position of this center of gravity. And that is what they want. So the value of D is what they want, and that's what we have to look for. Then there is tension in this string, so the arrows must point towards each other, and this string is inclined at an angle of 30 degrees to the vertical, as it was said in the question. And because this is 30, this will also be 60. Then this one also there is tension, that is why the arrows are pointing towards each other. And this is 40 degrees to the vertical, meaning the remaining one will be 50, and this side it will be 130, because 90 plus 40 is 130. So with that we can resolve vertically, horizontally, and also take moments. So let's begin by resolving horizontally. When I resolve horizontally, I'll come up with T1 cos 60 is equal to T2 cos 50. Now we are dealing with forces acting on the rod, so the forces of interest are these ones, only those acting on the rod. So these ones are the ones we are interested in. So when I resolve horizontally, this angle is 60, meaning that when I resolve T1 to the horizontal, it will be T1 cos 60, and this one to the horizontal, it will be T2 cos 60. So I can choose to make T1 the subject, and that will be that. The next is to resolve vertically. So when I resolve vertically, I'll come up with this will give me T1 sine 60, and this will give me T2 sine 50, and this will just give me this because it's entirely vertical. So before we go to the next slide, let's see how marks can be awarded for this slide. So B1 for the correct force diagram drawn using a ruler, B1 for resolving horizontally, and B1 for resolving vertically. So I think we realize that these are two equations and two unknowns. Therefore, when I substitute the first equation into the second equation, I'll come up with that, so that I have only one unknown, which is T2. Therefore, my aim is to make T2 the subject, and T2 will be equal to 41.7158 newtons. Then next is to take moments about A. When I take moments about A, I'll come up with this 78.4 times D is equal to T2 times 5 sine 130. So let's see how this comes about. So remember, in the previous video we saw that the formula for taking moments is FD sine theta, where D is the distance from the pivot to the point where the force starts from, and theta is the angle between the rod and the force, and F is the force. Therefore, when I stand here, the force is here, that is F, and it starts from this point, meaning the distance from pivot to the point where the force starts from is D, which is that. So I'll say force times D sine theta, where theta is 90, but remember sine 90 is equal to 1, that is why we can just simply write 78.4 times D. Then for this force, it starts from here, meaning that distance from pivot to where the force starts from is 5 meters, and the angle between the force and the rod is 130, and the force is T2. Therefore, the moment will be T2 times 5 sine 130 degrees. So that is where that statement is coming from. So the good thing, I already know the value of T2, so I'll come and substitute for T2 and remain with D as the only unknown. Therefore, when I make D the subject, it will be 2.0380. Therefore, I can come and conclude that the distance from A, where the weight of the ladder of the rod acts, is 2.038 meters. So basically that's what they wanted. Now let's see how much can be awarded. So M1 for substituting for T1, A1 for the value of T2, M1 for taking moments, and A1 for the value of D. So that was question 5. Now we shall go to question 6. So question 6 says, a uniform rod AB of mass 2.5 kilograms is balanced in space by two inelastic strings AP and BQ. String AP is horizontal and BQ makes an angle theta with the vertical, and the rod AB makes 30 degrees with the horizontal. Now the good thing, they have drawn for us a sketch. Find Roman 1 the value of theta, and Roman 2 the tensions in the two strings, the tension in this string and the tension in that string. So we have to first redraw the diagram, then we can show the forces acting on the diagram. So let us first redraw. So now we shall show the forces. The first thing to put is the weight, because it acts vertically downwards, and it will be 25 G. The next is to show the tension. Tension arrows must point towards each other. Then also at this point there will be tension and arrows must point towards each other. So next is to take moments about a convenient point. So in this case we shall take moments about B, and we shall let the length of the rod be to L because they didn't give us the length, so you have to let it to be a certain letter. So when I'm taking moments, still the formula holds. It has to be FD sine theta. So when I stand at B and I want to take moments for this force, so this is the force, and that is F. Now D is the distance from the pivot up to where the force originates from. So this is the pivot and this is where the force starts from, and that distance is what we shall call L, because the ladder was uniform, meaning that this is L and also this is L. Then the angle between the ladder and the force, you can either use that or this, because both are this angle and this angle, they are between the ladder and the force. So because this one is known, I'll use this one, and that is why I'm putting there sine 60. Then also take moments for this one. So the force originates from this point, and because this is the pivot, the distance from the pivot up to where the force originates from is 2L. That's why you see here 2L. The force is T1, and the angle between the force and the rod is 150. That's why you see sine 150. So when next you substitute for G, and also realize that L cancels, then from there T1 will be the only unknown, and T1 will be equal to 21.218 newtons. So we have been able to get the tension in string AP. We are left with tension in string B2. Now before we get tension in string B2, let's see how mass can be awarded for this slide. So B1 for the correct force diagram drawn using a ruler, M1 for taking moments, A1 for the value of T1. So we are going to resolve horizontal. When I resolve horizontal, I'll come up with T2 sine theta being equal to T1. And when I resolve vertically, I'll come up with T2 cos theta equal to 2. So next is to divide equation 1 by equation 2 to come up with that. So this T1, T2 cancels. This gives you tan, which is that. And this is T1. We already got T1 in the previous slides. So we substitute for T1. I also, this G is 9.8, therefore theta is the only unknown, and to be equal to 40.8 degrees. So now that I've got theta, I can be able to get the value of T2. So I'll come and say that from equation 1, T1 is that and theta is that, therefore T2 is the only unknown, and to be given equal to 32.413 newtons. So basically that's what they wanted. Now let's see how mass can be awarded. So B1 for resolving vertically and horizontally, M1 for division, A1 for the value of theta, M1 for substitution, and A1 for the value of T2. So that brings us to the end of this video. Thank you for watching, and be reminded that the next video will be on moments and couples. So if you are not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video on moments and couples has been uploaded. Otherwise, thank you for watching, and also if you know of any student who is not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that we can all benefit as a family.